Everyone being here. It's nice to see a full room, and yeah, thank you to the organizers for inviting me and hosting me, and yeah, it's been really lovely to visit the group here. It's been very stimulating, really amazing to talk to everyone, and especially thank you to everyone who presented earlier today. I think that's been a nice sort of lead-in to what I'll talk about, which is, yeah, intersection patterns of convex sets. The sort of motivating question we have here is families of convex sets in RD, how can they be arranged relative to each other? And of course that's pretty vague, as I've written it on the board, so I'll talk about two kind of ways to make this precise. One a bit more classical, people might be more familiar with it. Another one that's a bit more recent, but I still think quite interesting, and there's some open problems in both cases that, yeah, to me I think are pretty motivating or enticing. I hope some people will be enticed and make some progress on them. But yeah, we'll see. And okay, I think we've been talking about convex sets all day, so I don't need to remind people of what they are, but just for the sake of completeness of the recording or something, we can look at some sets and see which ones are convex. So yeah, convex sets, right? Any 2 points I choose, the line segment stays in the set. So this would not be convex. My star is not convex. If I bend a line segment, that's not convex. Empty set's okay, etc. And let's just recall one kind of classical result about arrangements of convex sets. So Helly's theorem, and I put the date here or the year here to emphasize how long this has been studied for. All it says is that if I have n convex sets in d-dimensional space, and every d plus one of them that I choose has a common point, then all the sets have a common point. And of course, as this audience is probably familiar with, there's many generalizations of this, right? There's colorful versions, topological versions, then applications of all these different versions to different combinatorial problems, and so on and so forth. So this is a really rich field of study. It's still very active, right? We heard a presentation earlier today from Ming Qi where a Helly-type theorem appeared there. That was one of the results, and this is something that still is actively being explored. And I'm going to introduce some kind of terminology and a bit of definitions and framework to kind of situate this type of theorem. Okay, so I'll pull down my last board, and I'll give us our first definition. So I have a collection of sets, right? In Helly's theorem, I have n sets, convex sets in RD, but this definition could apply in other contexts as well. And what I want to record is how they're arranged, and what I mean by arranged here is how they intersect each other, right? So the nerve is going to tell me this. And it's going to be some simplicial complex where for every set I get a vertex. And which faces do I include? Well, I include a face sigma, which is a subset of 1 through n, exactly when the intersection of the corresponding sets is non-empty, right? Okay, so here's an example in R2. I have 4 convex sets, U1, U2, U3, and U4. So for each of my sets, I get a vertex. And which faces do I fill in here? Well, I see 1, 2, and 3 all intersect, so I'll fill in this triangle. And you'll notice this really is a simplicial complex, right? If some sets intersect, and then I intersect fewer of them, then I'm still intersecting, right? And okay, I need to add one more thing to make my nerve here. I see 3 and 4 intersect, so I put this edge. Okay, and that's all. Great. So this is the nerve of that collection of 4 sets in the plane. So I want to study how sets can be arranged, convex sets, and if this is my notion of being arranged, the combinatorial type of an arrangement, then what I'm asking here is which simplicial complexes can I get as a nerve of convex sets? Okay. So again, just the definition here. asking a realizability question here. If you give me a simplicial complex, can I find U1 through UN, a convex set in RD for every vertex, so that the nerve I get is delta exactly? Okay. So over there, that complex is 2 representable, right? It's a 2 representation, but actually I could even do a 1 representation, right? So I have my 3 intervals intersecting, and then a 4th interval that touches the 3rd, but not the 1st or 2nd. Great. And okay, this vocabulary that we're introducing is kind of nice, because it lets us actually rephrase Helly's theorem, right? What is Helly's theorem telling me? All it's saying is that a d-representable complex is determined by its d-skeleton. Once I know the d-skeleton, I know the order d+1 intersections, and that's enough to figure out the higher order intersections as well. Right? Okay.
By d-skeleton, you mean the sets of size at most d?
At most d+1. So here I mean d-dimensional skeleton. Yeah. So if I'm 2 representable and I know the triangles, then I know the rest. Great. And actually, you can say something slightly more than this. So I won't get into the details here, but let me just mention. So d-representable complexes were shown to be something called decollapsible quite a long time ago. And what does this mean? Well, if it's decollapsible, it turns out the same thing is true. The d-skeleton determines everything. But this is a slightly stronger notion where you have some ordering that you use to decompose the simplicial complex sort of face by face. Okay, so this is a slightly stronger notion than that. I just want to mention this briefly because I'll say something about decollapsible complexes later, but the precise definition here I won't get into just for time reasons. Okay, so I want to switch gears just very slightly. We can think of this Helly theorem, or this reinterpretation of it, as kind of a restriction on d-representable complexes, right? It says that, not every complex can actually be, represented in dimension d, and it tells you some structure that you should look for to tell whether or not a complex is d-representable, perhaps. So let's look at the opposite side of things. If I have a complex, maybe I want to know, positive results, right? When can I actually form a representation? Maybe how big does my dimension have to be before I can find a representation? So this result was actually discovered twice independently in 1967 and 1985. And I'm calling it a positive result because it's constructive, right? It says you can do something. And what it says is if you have a d-dimensional simplicial complex delta, then it is representable in some dimension. And okay, that dimension, the best we can do is 2d plus 1. So I might have to make the dimension much larger, but eventually I can find some convex sets, so that's good. Let me also just briefly mention here. So for any d, there does exist a simplicial complex where 2d plus 1 is the best you can do. Okay. So we can't hope to improve this theorem, but still it's something nice for us.
Do you know what's the example?
What is the example?
Yes.
So if you take the full d skeleton of a simplex on 2d plus 2 vertices, I think it is. Basically, just take the full skeleton of dimension d with enough vertices, then you can only represent it in dimension 2d plus 1. So it's kind of like an embeddability of a simplicial complex obstruction that's happening there. And I guess the other thing I'll just gesture at, and again, I won't get into the details, but why is this the dimension? What's the construction you use? Well, you take a cyclic polytope in dimension 1 higher, and okay, then you take its dual, and then you project through a facet into the smaller dimension, and by neighborliness of cyclic polytopes, you have enough freedom, basically, to find your convex sets. So this is the reason you can do this is sort of a neighborliness of polytopes reason. Okay, so the reason I want to set up these two results is that I want to sort of ask a slightly different question about these d-representable complexes. So we have, one thing that tells us that there's not too many of them, right? And another thing that says, okay, there are some. But let's try and quantify that a bit more precisely, right? So I'm fixing my dimension, and then I'm letting the number of vertices get large, and I want to know how many d-representable complexes I get as n gets large. And of course, I'm not going to give you like a precise formula or anything, but I want to give some estimate that's at least a little bit substantial. Is the question, as I posed it, clear? Great. So just a note here. So d equals 1 is actually just counting interval graphs. If I know the intersections of intervals, then pairwise, then I know the whole complex they represent and vice versa. And so yeah, this is actually a question that has been studied before in the d equals 1 case. For d is 2 and higher, it hadn't been looked at. But there is some related literature that I'll just mention if people are interested. And I guess a couple of prototypical examples would be counting the number of polytopes on n vertices for a fixed dimension. Again, not precisely, but in some asymptotic fashion, and that's been studied since the 80s. Or counting the number of d-dimensional spheres, triangulated spheres on n vertices. Again, this is something that's been studied very classically, but actually there's been recent progress as well. Going back to 2016 for the, I think, odd dimensional case. There's also been work by Novik and Zhang recently on centrally symmetric and neighborly spheres. So again, this is kind of an active area of research. And I'll maybe jump straight to the conclusion we're able to make in the case of d-representable complexes. Before I state a theorem, let's use these theorems that we already have to at least say something. I can get some initial bounds from this construction and also from Helly's theorem. So Helly's theorem tells me once I know the D skeleton, I know everything. So that tells me that the number of such complexes is at most the number of d-dimensional complexes, right? And that's an exponential function in a polynomial of degree d+1, right? And we can get a lower bound of, the same kind of thing. I can choose an arbitrary complex of dimension at most, d/2 rounded appropriately, and that will be d-representable, so I have some freedom there. And of course what you notice here, right, is these exponents are very different orders, right, d+1 versus d/2, and the reality is going to lie somewhere in the middle. When we started working on this, it wasn't clear whether it should actually be one of these two possibilities. I almost want to take a poll of who thinks, which of these should be true or should it be in the middle. I don't know if anybody is willing to volunteer a thought about this.
Well, even for the case when D's 1, it's in between, right?
Sure, okay, so if you, yes, this is actually a good thing to observe. If you go to interval graphs, so what's the answer there? It's actually n log n. So it's not n squared, and it's not n. Okay, so maybe that helps guide us, right? It should be in the middle somewhere, and okay, I'll spoil it, it is in the middle. And we're able to say exactly what the exponent is for every possible dimension. So yeah, indeed, this one-dimensional case of n log n, generalizes to higher dimensions, and what you end up with is just a n to the power of d, and again, a log n out front. I won't get into the details about how to prove this. Actually, I think I'll be speaking about this in Seoul next week, so if you want to know some of the proofs, then maybe I invite you to join me there or to talk after the seminar today. But something I do want to add here, I mentioned decollapsible complexes earlier as well. So you could, of course, ask the same question, how many decollapsible complexes are there? And we're able to get an answer there as well, and actually it's a different exponent, right? This upper bound from Helly's theorem is the correct answer there, and a consequence of this, right, is that these d-representable complexes, these more geometrically arising kind of complexes, are actually vanishingly small as a class compared to the decollapsible complexes, right? So collapsibility, somehow representability is rare even for collapsible complexes. Yeah, I think my last couple things I want to say about this before I, again, switch gears a little bit is, what are the open questions here? Okay, obviously one is we don't know the constants on these n to the d plus 1s or n to the d log n's. Maybe optimizing constants seems a little bit tedious, but I think in this case actually understanding what the constant is would be nice, because again we have an upper and lower bound for the constant, each of which are arising from some geometric argument. And so again the sort of philosophical question there is which of these geometric things that we're looking at is the correct one? What's the reality there? What's the sort of essence of how these d-representable complexes look? I don't think we have a good idea of how to get that constant exactly, but that could be potentially interesting for either of these cases actually. The other thing I want to mention is that to get lower bounds for both of these quantities, we use a construction that's similar to split graphs, if you've heard of those, for constructing many chordal graphs. And a question that we could ask there is, does every decollapsible complex look like one of these? Almost surely anyways, with high probability. Mm-hmm. And again, for the d equals 1 case that's known, almost every chordal graph does split in this way. That's a classical result from, again, the 80s, at least I think the 80s. And for these higher dimensional, d equals 2, d equals 3, does the same kind of behavior arise, or is something changing once d changes beyond d equals 1? Okay. Great. So I'm going to change gears a little bit. Any questions about this before I do?
Can you at least say a couple of sentences of how you prove the upper bound?
Yeah, so the upper bound is kind of interesting. Okay, so this upper bound is easy, because the D skeleton tells you everything. This upper bound, for a while we were kind of stuck on that, and eventually what we realized is that you can take your D representation and look at all the, now instead of D plus 1 fold intersections, look at all the D fold intersections, and project those to a one-dimensional subspace. Now you get intervals, and you have order n to the d many of them, and you have a one representable complex in this one-dimensional subspace, and then we prove that that one representable complex recovers the original one. So somehow what I'm really saying here for the upper bound is that the number of d-representable complexes on n vertices is at most the number of one representable complexes on n to the d vertices. Okay, roughly, up to constants and so on. So we construct an injection to one representable complexes on more vertices. Yeah.
Is there some kind of speed theorem where I think Bolovas or somebody had a theorem that any hereditary graph classes has only 4 kinds of growth rate?
Oh.
And I'm wondering whether a similar phenomenon could happen for complexes.
That's actually a good idea. I don't know, but maybe that would be a proof worth reading to see if it would generalize to complexes, or set systems or something.
Yeah.
I think that would be a good approach, but we haven't tried it.
So
Great. So I'm going to forget about d-representable complexes for a little bit. And to sort of switch gears, I want to give a motivating example where I think d-representable complexes or nerve complexes are, not telling us information that we might be interested in. So let's look at some arrangements of sets in the plane. Okay, so in each of these cases, I drew 3 different convex sets. And what you'll see is they all have the same nerve, right? The sets always triple-wise intersect. But really, I mean, these pictures are quite different. And maybe I want to understand that. I want to, I care about the difference between this and this somehow. And I want a framework that actually allows me to care about that difference, where nerves, right, don't let me do that. So these arrangements all have the same nerve, but there are some differences between them, and maybe I, in some context, I'm going to think that those are, important differences. So how can I modify my framework for d-representable complexes to capture this? Well, here's a simple definition. So I'm going to, again, take my collection of sets and write down some set system, but it won't be a simplicial complex anymore. It'll be something else. And again, I have to tell you, which subsets of 1 through n to include, and here's my criteria. So I've written down formally what I'm going to define this as, but let me just say what it means in a more informal sense. I look at every point in space, and I write down at that point which sets it's contained in, and I get some label for that point. Then I just collect all the labels I get that way, right? Okay. And of course, this is more general than the nerve, right? Because the inclusion maximal labels I get are telling me the facets of my nerve. And the other kind of way to think about this, okay, the nerve told me intersection information. The code is telling me intersection information and covering information. It's telling me how intersections get covered by other sets potentially, not only which intersections are non-empty. Okay. So let's just look over here and do maybe 1 or 2 examples. So if I have my sets U1, U2, and U3, then when I'm in here, I'm labeling with set 2, right? Here I'm labeling with 1, 2, 3, 2, 3, 3. Out here I label with the empty set, and so on. Okay. And again, I'll ask this realizability question. Given a code, find me the sets that realize it, or can you? And this question was first posed actually quite recently in 2013 by Kurto, Itzkov, Belly-Scuba, and Youngs. They have this word open here. They're using now not just arbitrary convex sets, but open convex sets. For d-representable stuff, didn't matter if I used open or closed or anything else, the question was the same. You can always reduce even just to compact sets. Here, actually, this openness turns out to be kind of a subtle problem, or a subtle, change here. The reason they asked about open sets is they were motivated by some neuroscience question, and they wanted the sets to really be, full dimensional. But it turns out that the answer to this question changes if I write the word closed there. There are codes which can be realized with open sets but not closed sets, and actually vice versa. There's codes that can be realized with closed but not open sets. Okay. So let me just define a couple parameters here for the sake of bookkeeping. I'll say the open embedding dimension, or ODIM, of a code is the smallest dimension where I can realize it with convex open sets, or infinity if there's no realization. That can happen as well. And likewise, I'll define the closed dimension. To be the same thing with closed sets. And let me just give one example where these two quantities are different to convince you that that I really need both of these parameters. So here's a code. I'm going to have, if I make a realization, 4 sets, and I want these code words to show up. And let me just highlight for us maybe the maximal code words, because those tell us the intersections. So the first 3 sets intersect, and then each of these sets intersects with the 4th set, but only pairwise, and that's it. And this is not a simplicial complex, you'll note, right? Because I'm missing the pairs 1, 2, 1, 3, 2, 3. And okay, let's start with a closed realization. Does anyone see how to draw a closed realization in, let's say, R2? Okay, I see people doing it with their hands, and yeah, good. So I could take sets 1, 2, and 3. They all needed a point, so I get my code word 1, 2, 3, but I don't get pairs, right? Because any intersection of these two is covered by the 3rd set. And then my 4th set just does this. Okay. Oh. Great. And you can convince yourself pretty quickly this is not realizable in R1, right? So here, my closed dimension is 2. And you might expect, okay, open dimension should be 2 as well. Just take these lines and thicken them a little bit or something. Turns out this doesn't work. The reason is that around this point here, you'll end up with pairs, no matter how you thicken your sets. And so it turns out to be true that this thing does have open dimension equal to 3. And again, if I can maybe draw us a picture, but you can also just do it with your hands, right? 3 sets orthogonal coming out of a cube, and then a 4th set that comes in sort of along the all ones vector or something and hits them all. there's my sketch. And it turns out this is true in general. You can have something like this where, let's say the first n of your sets are all behaving in this way where they have a central meeting point, but then otherwise you'd only see singletons. And then you have a final set, an n plus first set, that touches them all, but it doesn't touch this central region they all intersect. And that, of course, you can do in R2 very easily. Right? You have a bunch of lines passing through a point, and you cut it, but it turns out the open dimension is n. It's the number of lines. Okay. So I think my abstract promised a Helly-type theorem, and maybe this counts as a Helly-type theorem. It's kind of a strange Helly-type theorem, right? Because it's not about the intersections, it's also about coverings. I need open sets, because if I do closed sets, it's failing, right? But there's some relationship between the dimension and the intersection pattern, and,
Well, what is the Helly-type theorem?
Okay, maybe let me, I have time to write it down precisely, so let's do that. I think it's worthwhile. Because I vaguely gestured at it, but yeah, let's. So here's my setup. I have my, d+1. I have my sets in RD. I have actually d+1 of them. And what do they do? Well, the code of these collection of sets behaves as follows. I have all the sets intersecting. Otherwise, I just have singleton code words. I'm deleting some parentheses here just to save time. And I have the empty code word. And now what is my conclusion here? So it's going to sound a little different than what we saw over there, but I like this phrasing. I'm choosing one point from every one of my sets, and then I'm taking the convex hull of those points. And my claim is that that convex hull actually hits this central region where all the sets intersect. So let's look at this in R2, just as an example. So I have, if D is 2, 3 sets, and they behave in this kind of way like this. So they're all intersecting in here, and otherwise I only see one set at once. And now if I choose any 3 points, one from each set, right? I can choose maybe here, here, and here. Then this triangle really does intersect that central part. In other words, if I tried to draw this code in R2, I could choose a point here, and a point here, and I'd get a code word that I shouldn't have. Great. And there's other kind of ways to phrase this theorem, a number of equivalent versions. I have one other thing I'd like to say, but the last comment I'll make about this is that there is a slight generalization of this theorem. So the proof of this uses actually Rodin's lemma, plus some fiddling with the open sets. And you can use actually Tverberg's theorem, right, which of course generalizes Rodin, and prove a more general version of this type of theorem as well. Okay, so big picture, let's take a step back for a second. We have this framework of looking at codes, and we're seeing that it's quite different than the study of d-representable complexes. for one, open versus closed matters, which was not true before. I want to highlight a couple other, I think, kind of interesting differences that this framework has as compared to d-representable complexes. So for d-representable complexes, right, for every complex I could realize it, I could represent it in a dimension 2D plus 1, which is linear in the number of vertices, right? It turns out this is no longer true for codes. If I can realize it, I might be forced into even an exponentially large dimension in terms of the number of sets. Here actually, my guess is the same should be true for closed sets even, but I don't know a family where this happens. That's one open question that I want to mention just very briefly. But maybe the main open question I want to kind of end with here is the following. Okay. So let me state a result and then ask a question that's sort of motivated by that. So it would be nice to understand the relationship between open and closed dimension, right? But it turns out there's not a relationship in general. For any A and B, at least two, no matter how different they are, even if one or two of them is infinity, I can find a code that has open dimension exactly A, that's the smallest I can get away with for open sets, and closed dimension exactly B. And okay, there's even slightly more you can say, but this is the main thing I want to say here. So what does this tell us? It tells us there is no relationship in general we can expect between these quantities, but for certain types of code, maybe there is. For example, if your code, the intersection of any two code words is still a code word, it is true that the closed dimension is bounded above by the open dimension. Okay, so there's certain things you can say like this. And one that really has eluded me, but I think should probably be understood, should be understandable, is the following question.
Size is the number of sets and
Number of indices in a code word. So for example, in this code, all my code words have size 3 or less. So yeah, I'm only...
So the size is 3.
Yes.
Okay.
And yeah, the way I'm phrasing the question, so I have all open convex codes, but I'm only looking at the ones where the code words have size 3 or less. And my question is there a uniform upper bound on the open dimension? Or the closed dimension, but I think open dimension is maybe the one that I have some potential ideas for here. What I'll end with, what I'll conclude with is just a comment about this. So for d-representable complexes, right, if all my faces have size 3 or less, then that means my complex has dimension 2, so I can do it in dimension 5 or less. So there is a uniform upper bound for d-representability once I fix the size of my code words or size of my faces. For codes, my guess is that the answer should be no, but we really don't know even any code like this that goes beyond that dimension 5. I can't beat 5, I can't get 6. What I will say is some recent progress on this. So this code here shows that among these types of codes, there can be a gap between closed and open dimension. But what type of gap can exist? Well, some work I did with some students this summer actually shows that not only can I have a gap of 2 versus 3, I can have a gap of closed dimension being 3 versus open dimension being either 4, 5, or 6. We don't quite know. But there can be a gap even when the closed dimension is getting a little bit larger. And what we really want, of course, is just to beat this bound of 5 and really in general show that there should not be a uniform upper bound like this. I think, there are some kind of candidate codes that could go in this direction, but I think you would need to know a lot about sort of discrete geometry theorems that I maybe haven't been able to find yet to make progress there. So if anybody would like to talk about this question, I'll be around for another week, and I'm very happy to chat about it, share some of the ideas I have, and I think that's where I should end.
Is your code world must contain an empty set? If not, just in the RD is a connected set, if we consider an open dimension, and if your code world is just a 1 and 2, then it means RD can be partitioned into 2 open sets, but it is a contradiction. So.
Yes, so you're asking, okay, so I think what you're getting at is that I need to restrict to open convex codes. So there are codes that can't be realized with open sets. For example, I think the one that you just suggested is like 1, 2, 1, 3, empty set. So here, the first set would be a disjoint union of the second and third. That would be bad. This is not realizable. So, okay, forget about codes like this. Then ask this question.
That's just realizable.
Yeah, so I'm only looking at the, here I mean, open convex, realizable. Because yes, otherwise it would break.
So open convex code means it's realizable by open convex sets.
Yes, in some dimension. Yes, sorry. Yes, among all codes, realizable by open convex sets.
Okay.
And having code words of size 3 or less. Can you find a uniform upper bound on these things? Or really, I think we should prove that there isn't.
You're
a
really
uniform
interested in
upper
open convex codes and what is an upper bound on O.
Yes, sorry, yeah. So I guess this, you could ask for closed and put closed here as well, and I don't know the answer there.
So I'll ask a question.
Yeah.
So I believe Tanser or maybe Uli Bogers, they have results like the algorithmically determining if a complex is the nerve or something, right? So determining whether it's d-representable.
Yes.
I think there are results like this. But what about determining if the code word is open realizable?
This is my final slide that I didn't get to write, so I'm glad you asked. It's a really natural question, right? Given, is there any algorithm at all to decide if a code can be realized, let's say in dimension 2 or 3 or whatever. And in some recent work with Boris Book, we showed for dimension 2, there is an algorithm, it is decidable. It's like NP hard and it's horrible, but theoretically there's
okay,
a
so
way
there's
to
some
approach it.
undecidability result higher up or something like this.
For d = 3, we really don't know. And our techniques break in at least 2 separate places for d = 3. Boris is, I think, fairly convinced that it should be undecidable in dimension 3 and higher.
Because that's what you get for the nerve, I think. There are undecidability results there, right?
So for d-representable, it is decidable for all d. And the reason you can bound the number of hyperplanes you need, and then it's a question in the existential theory of the reals with some, with some nice bounded description. I think undecidability,
That's for embeddability.
maybe it's for embeddability, or I know contractibility is
Yes,
undecidable,
yeah.
right?
That's usually one you reduce it to.
Yeah.
Oh, okay.
So if you don't put restrictions beyond convexity on your realizations, so I get like a notion of dimensions just regardless of what your sets are, would that be somehow related to like the minimum of open and closed dimension, or can they also wildly diverge?
Can you ask your question, or can you restate the first part of your question? So you're
So if you don't put open or closed, but just
Mm.
allow any type of convex
oh
sets
yes, I see.
and
Yeah,
define a dimension like this, would this dimension be like tied to a minimum here, or can it arbitrarily diverge?
So I guess what's known for any convex sets with no restriction is it is realizable in some dimension, no matter what your code is. So that's good at least, or maybe it's good. My guess is if you defined an embedding dimension like this, probably the gap can still kind of be arbitrary. I will say the upgrade to this result is that if I choose a number c, which is larger than the maximum of these, or at least the maximum, then you can define another embedding dimension where you want a realization that is robust in the sense that you can switch to interiors or closures and the code doesn't change. So obviously that's like the maximum of these two, because such a realization gives you an open and a closed realization. That's at least the maximum, but it can be much larger than the maximum as well. So there's really no control on the relationship there either. So my guess is that there shouldn't be any if you go sort of down in this other way, but I don't know.
So this theorem there, can you choose both A and B to be infinity?
Yes. Yeah. So I guess that would be.
I guess that would then okay.
Yeah.
So this would then be realizable with any convex sets, but neither with open nor with closed.
Sure. Yeah.
Okay.
So that tells you, I guess, something is bad happening already.
Okay.
Yeah. And even when they're finite, my guess is it's still something, but you can still get an arbitrary disparity.
So the question, I think it's related to his question.
Mm-hmm.
Do you ever consider, okay, there are two questions. Do you ever consider code words that don't have the empty set? So like you're using, among your sets, there are half spaces such that you somehow cover the whole space.
Yeah, this is a slightly controversial. It's something I typically ignore.
That's
So once you
fair.
have the empty set, you can reduce the bounded, and life is good. If you don't have the empty set, you're covering the whole space, and that's kind of like I think, so Boris and I in our paper, we didn't prove decidability for such codes, but I think we convinced ourselves that it's decidable in dimension 2, even if you don't have the empty set. But I guess the caveat of our result is that we do assume the empty set, and I generally do in the results I've stated. If you don't, then basically what you're asking is, again, take like a large enough ball that it contains all the code words. You're asking about how to cover one convex set with other convex sets. And so I think this would be, so maybe this is equivalent to something I have studied, which is with Belonovic, we studied convex union representable complexes, which are basically nerves of covers of convex sets by convex sets. So I guess you're asking the code version of that.
Right.
And I don't think I have any like amazing examples off the top of my head, but I guess by nerve theorem, you know it's going to be contractible, and then actually it's going to be collapsible and so on. So you can start to say things like that, but I think it would be, it gets pretty hard, I guess.
One last question. That's two parts. Splits in two directions. So one would be, have they studied for, so in discrete geometry you often have more specialized results when you specialize the sets. For example, half spaces or disks or semi-algebraic sets is another one they like to use.
Sure. Yeah.
And has this theory been studied for those kind of sets?
I would say it's understudied, but it has been studied a little bit. So there was a paper about using half spaces, but I forget what results they proved. I don't know if they had like a super robust set of results or if they had anything that was like really, I'm struggling to remember what about the results was strictly stronger than the usual convex case. The other thing that has been studied, so for another summer project last summer with some students, I studied access parallel boxes.
Okay. Yeah.
And there it's not hard to write down a combinatorial characterization of which codes can be realized in terms of, interval codes, basically.
Yeah, right. Okay. Okay.
So there's something you can say there. I guess, you mentioned spheres or circular
Yeah.
balls. That would be interesting, but I think it's not very well studied.
Mhm.
There are classes of codes known to be realizable by balls, but they're pretty special. Like they're very, very special classes of codes arising from portal graphs plus some other ingredients.
Mhm.
But I think there's a lot of open questions there.
Okay.
Any other questions?
I saw you had one.
I mean, it's the same questions.
Oh no, hit him.
Oh.
Sorry.
Oh,
I was wondering about, related to the decidability, if you can say something, if you restrict to things with a bounded number, constructed from a bounded number of balls with the intersection and convex hull. How,
Yeah, so I guess once you restrict to sets with some nice enough, bounded enough description, then probably you can get decidability. I guess one open question in that direction, it's not quite answering what you asked, but I think it would be interesting, is, okay, in R3, we don't know how to do it in general. Can you prove decidability in R3 for like a special class of codes, like, for example, codes that have code words of size at most 3? I would like to know that. Or intersection complete codes I mentioned earlier are another kind of well-studied or nicely behaved set of codes. Can you prove decidability for those? I'm not sure, but maybe that would be a place to kind of get a foot in the door at least.
for the case of the plane, could you use that some finite description is sufficient, or something else?
Yeah, so the proof basically goes, you reduce to polygons, which we can't do in higher dimension, and then you prove the polygons need only a bounded number of vertices, or a computable number of vertices, again, which we can't do in higher dimensions. But once you have that, then it's a question about finding, finitely many coefficients for the hyperplanes that describe your sets, and you know how many coefficients you actually need to look for. So it's a finite problem in, real polynomials. So it's okay.
Any? If not, let's thank the speakers.